what is happening to nitrogen levels within Arctic watersheds? Well, as it turns out, Arctic rivers are delivering less vital nitrogen as climate change alters water chemistry. Oh, friends, Jim here. This is important. It has major implications. So what's going on? We'll return to this figure later on. But climate change is starving the Arctic Ocean of essential nutrients. Right? You know, they're looking at the Ob, the Yenisei, the Lena, the Kolyma, the Yukon, and the Mackenzie rivers. They all empty into the Arctic Ocean. Well, except the Yukon, it enters into the Bering, so not technically the Arctic Ocean, but still high latitude. Mackenzie River Delta is right here, right into the part of the Beaufort area I'm familiar with. So, climate change is starving the Arctic Ocean of essential nutrients, with the region's 6 largest rivers now delivering far less of the type of nitrogen that marine ecosystems need to survive, according to new research in one of Earth's most vulnerable regions. Nitrogen that marine ecosystems need to survive. Right? Hydrogen, oxygen, nitrogen, carbon are the most common elements found in organisms. And the nitrogen usually has to be in the form of a nitrate or a nitrate, or you can have other forms that certain bacteria convert into a usable form for plants and primary producers. But nitrogen is essential. I mean, you can spend a whole week, and you do, in ecology classes discussing nitrogen cycles. The study, led by Bridger J. Rule of NYU Tandon School of Engineering, is published in Global Biogeochemical Cycles. Rule completed the research as a postdoc fellow at the Carnegie Institution for Science. The study found that warming temperatures and thawing permafrost are fundamentally altering the chemistry of Arctic rivers. The result is that coastal food webs that have sustained indigenous communities for millennia are being deprived of inorganic nitrogen, an essential nutrient, potentially triggering cascading effects throughout the Arctic Ocean ecosystem. Let's highlight that. Result is that coastal food webs that have sustained indigenous communities for millennia are being deprived of inorganic nitrogen, an essential nutrient, and this has implications throughout the Arctic Ocean ecosystem. This is a red flag. Rapid changes in river nitrogen chemistry could completely transform how these marine ecosystems function. The research analyzed 20 years of data from 6 major Arctic rivers: the Yenisei, the Lena, the Ob, the Mackenzie, the Yukon, and the Kolyma, which collectively drain 2/3 of the land area flowing into the Arctic Ocean. These rivers transport nitrogen that supports up to 2/3, 66%, of the ecosystem's primary production in coastal Arctic regions. Between 2003 and 2023, 20 years, Rule and colleagues documented declines in inorganic nitrogen accompanied by simultaneous increases in dissolved organic nitrogen, a far less bioavailable form of the element in 4 of the 6 rivers. Basically, plants or primary producers, they need the inorganic form of nitrogen where they can then within their own chemical factories in in cells and so forth to create the organic forms of nitrogen that they need in order to increase biomass. In other words, one would think, whoa, gee, it's already in an organic form. You would think, hey, great, just take this in and off we go. No, it doesn't work that way. They can't absorb it. They can't uptake the nitrogen when it's in organic form. It has to be in inorganic form. The findings reveal that warmer temperatures, increased precipitation caused by climate change, are driving the shift in nitrogen composition through the effects on river discharge and permafrost thaw. Using sophisticated statistical modeling, the researchers identified permafrost loss thawing, right, as the key factor explaining the diverging trend between organic and inorganic nitrogen in these rivers. They looked at 20 years of chemistry data, water chemistry data, with environmental variables including temperature, precipitation, land cover, and permafrost extent to pinpoint the climate drivers behind these chemical shifts. Land cover, I'm presuming snow. The Arctic Rivers research represented Rule's broader research mission to understand how human activity, climate change, and natural processes interact to affect water quality globally. He also goes on to look at PFAS contamination in drinking water. Okay. His research explores how human activity, the biosphere, and climate change affect water quality, with particular focus on developing analytical tools to quantify chemical contamination and developing models using remote sensing data to assess climate impact. River transport of nitrogen is estimated to support up to 66% of primary production in Arctic coastal regions, making these compositional changes important for marine food webs and the indigenous communities that depend on these resources. And of course, it goes to show how everything is interconnected. So now, let's take a look at this figure here. Okay. So, we're going from 50 to 80 degrees north latitude. So you can say, this is the Ob over here. That's the Ob River drainage system. This is over here is the Yenisei watershed. Then we have the Lena and the Kolyma. Over here we have the Yukon. And then here's the Mackenzie. So these are the rivers that were investigated. And so here we have blue represents organic nitrogen, red is inorganic nitrogen, and then the black line, we see here, right? That indicates the ratio. I'll explain that in a moment, what ratio precisely. Excuse me. So what are the units here on the vertical? We have dissolved nitrogen yield, and the units are kilograms per square kilometer per year. Right, so those are the units. And then we'll go from 2003 to 2023. And the ratio is the ratio of organic to total nitrogen. So in other words, to calculate this ratio, what you do is you go from the bottom to the top, and I'm looking at the Lena River as an example, and that looks like it might be about 80, 82 or so. Let's just say 80. I'm doing this just to give you an idea of how this is calculated. So that's the total nitrogen. So that goes in your denominator, 80. So what is and we're looking at the ratio of organic to total. So we need to measure the organic. Well, let's see. We go from where the red and the blue meet, and that looks like that's about, say, 20 or so. So if the total is 80 and this is 20, that means the organic is 60. So 60 over 80, that's 3/4. So that'll be about 0.75. And that gives you that point there. I'm just explaining to, the actual figures are going to be different, but I'm doing rounding estimate and just to illustrate how this is calculated and how these lines are generated. Now, what's really interesting is if you look in the Lena and the Mackenzie, some ways the Yenisei as well, we see a decline in the inorganic content, inorganic nitrogen. The organic, there's little dips and goes back up, but you can see that the organic, at least for the Lena, is considerably more than the inorganic. The OB, not surprisingly, you expect to see a ratio, especially right here, of under 0.5. If ratio 0.5 means that there's exactly, of the total nitrogen, exactly half is organic. You see that the OB has, and the Yukon has the highest levels of inorganic. But this is what they're measuring, and this is impacting marine coastal ecosystems. I'm not sure what the hash lines are for. They don't explain that. And the original paper is behind a paywall. So, but this shows you what's going on here. We're seeing considerably more organic, except for maybe the Yukon, which is almost pretty steady. This could be some basically annual fluctuations here. But what the point they're trying to make is that the inorganic amounts of nitrogen are declining, and is considerably more organic in most cases of the organic nitrogen. And this is not good for primary producers. So, it's not just, we're warming the planet and this is creating chaotic weather systems. It's everything else that goes with it. It's the impact on the chemistry, the geology. I've done a couple of videos now talking about how the warming Arctic or warming air temperature and changing precipitation patterns is changing what we see going on. It's changing the water chemistry, it's changing productivity, it could be changing ecosystem dynamics. So this is of major concern, and we definitely need to track this. Okay, that's what I have for you this time. Thanks for watching. We'll talk soon.